Okay guys, so I'm back on the Skittles problem and I have sketched my normal curve. Again, I put the population proportion that I'm assuming from my null value of 0.2 in the middle, and then I added 0.044 3 times and subtracted 3 times. Okay, so there's my typical normal curve. I labeled it. I would like to label where my sample proportion of 0.38 shows up. And I look at this and 0.38 is definitely higher than what I've got labeled on my normal curve. So I'm gonna go up a few more standard deviations, 0.332 plus 0.044. I'm still only at 0.376, so one more time, 0.044, 0.42. Okay, so I have on my normal curve here 0.376, and then 5 standard deviations above the mean is 0.420. Okay, so I can already tell that my sample proportion of 0.38 is a little bit higher than 4 standard deviations above the mean. So I know this probability is going to be really small, right? The curve is almost in line with the horizontal axis. This is going to be a super tiny probability, okay? But again, this green part is representing the probability that p hat is greater than or equal to 0.38, which is my sample proportion. Okay, so now let's actually plug our values in for z and find our test statistic. So I have p hat, instead of using 0.38, that's rounded, I'm going to use 31 out of 81. Minus my my population proportion of 0.2 and divided by that standard deviation, 0.2 times 0.8 divided by 81, and then take the square root. Okay, again, if I put parentheses around the top, I can put this whole thing into my calculator at once. So parentheses 31 divided by 81 minus 0.2 end parentheses divided by second square root of 0.2 times 0.8 divided by 81. Okay. All right, I get a z-score of 4.11, which is what I was expecting from my picture, right? I had to label 0.38 about just a little over 4 standard deviations above the mean. So now I use my z-score in table A2 to get my p-value. Oh, it does ask for my test statistics, so I'm going to actually state it. Z is equal to 4.11. I look at my table A2, that's a positive z-score. I come down here, 3.5 is as high as it goes. If it's higher than that, we have a left area of 0.9999. Now, obviously, that's not 0.9999 because that's not a left area. That's a right area. So I calculate this by doing 1 minus 0.9999, which is 0.0001. Okay, so essentially my p-value is approximately 0, right? Because really 4.11 is much higher than 3.5, so it is going to be even smaller than 0.0001. So approximately 0 is fine. Okay, so last part, based on the p-value, what conclusion should you make? So I'm just going to talk through this one instead of writing it out painstakingly in the video. Actually, I've already written it out over here, so I'm going to show you on my previous notes. I'm going to interpret the p-value first. Notice I put this in these green parentheses to indicate you don't actually have to do this, but it helps give you the idea of why we make this decision. So interpreting the p-value would be assuming you can't taste the difference in Skittles. So assuming that that proportion is 0.2. There is approximately a 0 probability that you get a sample proportion of 31 out of 81 or higher, remember, or more extreme, purely by chance. So that probability is so super unlikely. It's definitely less than 0.05, right? We're going to reject the null. We reject the null because our p-value of approximately 0 is less than the significance level of 0.05. If we reject the null, that means we do have convincing evidence for the alternative hypothesis that people are better at identifying Skittle colors than just guessing, right? That p is actually greater than 0.2. Okay, notice I put that into a context that your average person could actually understand. We have convincing evidence that people are better at guessing Skittle colors, or at identifying Skittle colors than just guessing. All right, we will do the last page in the next video.